Hey there, my name's Gary Sims from Android Authority. It seems today that everything has the word virtual stuck in front of it. We have virtual reality, we have virtual currency, we have virtual machines. Well, before any of those existed, we had virtual memory. And it's a technology that we use every day. You'll find it in Windows, in OS X, in Linux, in iOS, and of course in Android. So what is virtual memory and how does it work? Well, let me explain. So back in the day of 8-bit computers and today with microcontrollers, any app that's running, any program that's running on a CPU has access to the entire physical memory. And it basically assumes it's the only program running on that CPU. And so if it writes to a particular address, let's say address 495, that address is actually somewhere in physical RAM and it is address 495 and it writes something there. That's what goes. If it writes to a different address, it goes there. And there's a one-to-one relationship between the addressing of the physical RAM and the addresses that the computer program uses. Now that's fine when you've only got one program running, but when you've got two programs running, things now become a bit more complicated. First of all, you have to decide where you're putting each program in memory. Secondly, each program in memory has to be careful not to overwrite the data and the program used by the other task that's running. And thirdly, all addressing has to be relative. That means you can only ever say, do something 10 bytes forward from here or 15 bytes back from here. You can't use an absolute address like 4095 because that could actually belong to somebody else. It might not be your address. There's also the issue of memory fragmentation. If you're trying to run two programs and you allocate one bit of the memory for one program and another bit of memory for another program, and then what happens is the first program exits and then you try to write a second one, it might fit in that space of the first app, but maybe it's a bit smaller, so there's a gap left. And then when you run a third one, it can't fit in that gap, so it goes somewhere else in memory, and then you actually get these little gaps starting to appear, and so you get this thing called memory fragmentation. And that's a real problem. Eventually you'll run out of memory just because of fragmentation. So to get round these problems, we have this technology called virtual memory. And in virtual memory, each app that's running on a mobile phone, each program that's running on Windows or on OS X thinks it's the only app running. It thinks it's the only program running and it has access to all of the address space. In fact, it doesn't even have to have that amount of physical memory. On a 32-bit machine, that process thinks it has 32 bits worth of memory to play with, which is, of course, 4 gigabytes. And the way it works is this: when the app wants to access a particular address, there is a particular piece of hardware in the CPU called the MMU, the Memory Management Unit. And what it does is it maps from this virtual address that the app thinks it's running in to an actual physical address somewhere in memory. And so now the idea of partitioning up the memory is actually taken over by the operating system and the app doesn't need to worry. The app thinks it's the only app running, and it can write to whatever addresses it's allowed to, whichever memory it's been given to, and actually it doesn't care about other addresses from other apps because it's got its own virtual address space. So if we look at this diagram here, we can show that we've got app 1 and app 2. Now app 1 has an address space from 0 through to 524.2880, that's about 5 megabytes of memory. And I've also got app 2 with the same 5 megabytes of memory. And what you actually see is that although it's from 0 to there, in the physical memory, it might actually start at 524.2880 and it might run for 5 megabytes. And then app number 2 actually starts at 104.85760 and it runs from there for 5 megabytes. And the virtual address 0 in both apps is actually mapped to different places in the physical RAM. Now, because there's mapping going on here, the apps can be mapped to absolutely anywhere that the operating system wants to put them. So let's have a look at this diagram. So as you can see here, app 2 is as it was before. It's a 5 megabyte program from 0 to 524.2880, and it's been mapped over to an address in the middle there of physical RAM. But app number 1 has actually been divided into two parts, and the first half of it is mapped into memory before app number 1, and the second part of it is mapped into some memory after app 1. But App 1 and App 2 don't know anything about this. They just think they're running in their address space from 0 to the end of their program. So the advantage of the virtual memory system is each app is self-contained. It doesn't write over other apps' memory space because it has its own virtual address space. Secondly, it doesn't matter where the app is in memory because it is the MMU that does the mapping between those virtual addresses and the physical addresses. And thirdly, the app doesn't need to be in one continuous block in memory. It can be split up over many different parts, and this is the OS along with the MMU that makes sure that each address arrives at the right place in physical RAM, and therefore you get rid of that memory fragmentation problem. Now what I've shown you up until now is a one-to-one mapping, so that every time you have one particular address, there's a kind of a table that gets looked up by the MMU and it tells it where to put it in physical RAM. But the problem is, even for a 300 megabyte program, which really isn't that very big, you'll need about 79 million entries in such a lookup table to do such mapping. And obviously, if you've then got 10, 20, 30, 40 different programs running on your system, that's going to quickly turn into a huge amount of data. And there'll actually be no space left for actual programs because it'll all just be mapping information. So to get around this, the main memory, the physical memory, is divided into different blocks, and they're called pages, and typically they're about 4K in size. And so now using paging, actually you'll find that a 300 megabyte app only needs 77,000 entries in a lookup table, which at 4 bytes for every entry is about 300K, which is much more manageable. So now what happens when an app requests something from a virtual address, it actually goes to the MMU and the MMU finds out which page it's in and redirects it to the physical address of that particular page. However, what happens when the address is in the middle of a page? At the start of the page it's easy, there's a kind of a one-to-one lookup. But what happens if it's in the middle of the page? Well, actually what happens is that 4K is 12 bits. So the first 12 bits of the address are copied directly from the virtual address into the physical address. Then the remaining 20 bits are used as the page lookup. That 20-bit address is looked up in the page table. A thing called a page table entry is found, and that then gives you the 20 bits for the upper part of the address. And then the combination of the page address and the offset, those 12 bits, gives you an actual physical address in RAM. Now, one interesting question is, where are all these tables held? Well, they're not held in the CPU because even at 300K or 400K, multiply that by many processes running, and there's just not enough space in a CPU to do that. So they have to be held in RAM. Now that leads us to a kind of an interesting conundrum, because to access a virtual address, the MMU needs to access physical RAM to find an entry in the table, so it can then translate the virtual address into a physical address and then access RAM again. So you find there's multiple RAM accesses happening for one RAM access inside of the app, and of course that's going to be slow. If it's like 2 RAM accesses needed or 3 RAM accesses needed for each virtual address, then that's going to slow down your program by a factor of 3. So the way CPU designers get around this, they have a cache of recently looked up addresses. It's actually called the translation look-aside buffer, the TLB. And what that does is whenever there's address translated, it gets stuck into this cache, and then the next time an address is needed, actually it looks it up in the TLB. But of course, remember, it only needs to look up the page size. So if the program is running through the different instructions inside of one page, every time it goes to access it, it will automatically be a TLB hit because that page has already been found, and just the offset changes, which is absolutely okay. In some CPUs, in fact, the TLB is only 20 entries long. It might be bigger than that, maybe 64, 128, but you don't need that many TLB entries to actually increase the performance significantly during this lookup. So what happens if the MMU can't find an entry in its table for a particular virtual address? Well, in that case, the MMU raises a page fault and it goes back to the kernel saying, hey, I can't find that address. Now that can happen for one of 3 reasons. First of all, the app is actually trying to access an address which is not allowed to access. It hasn't been allocated that memory, and therefore Linux will just basically kill it off. You get a segmentation fault and the program just crashes and it just gets wiped out of memory because it's not allowed to access memory that it hasn't been given. In the second case, it could actually be what they call lazy allocation, which means that the kernel said, yes, you can have that, but it won't actually give it a physical page of RAM until it actually starts to write to it. And so in that case, the page fault happens, the kernel says, okay, I told the app it could use that memory, here is where I want you to put it in physical RAM, the MMU is reprogrammed, and then the whole thing starts off again, and the address is found in physical RAM. And the third thing that can happen is the MMU says, we used to have that memory, but actually now it's been swapped. And therefore the kernel will go and get that page from the compressed RAM, the Z swap that it's actually put it in earlier, it will uncompress it, it will put it somewhere in physical memory, it will reprogram the MMU and say, okay, you can now find that there, and then the whole thing carries on. And so there we have it, virtual memory. We've got a whole load of things going on here. You've got the virtual addresses, you've got physical RAM, you've got lookup tables, you've got an MMU, you've got the translation look-aside buffers, you've got page faults, and all this is being handled for you by the Linux kernel and by Android. So the next time you tap an icon to launch an app, just give a thought for all that's going on in the background, just so that app can be loaded somewhere into memory and it can run so you can make that little sprite jump across the screen. My name is Gary Sims from Android Authority, and I hope you enjoyed this video. If you did, please do give it a thumbs up. There's a link here in the description below which will take you over to the Android Authority forums, where if you want to speak to me about virtual addressing or virtual memory, please go over there and we can have a more detailed discussion than maybe we can have here in the YouTube comments below. Don't forget to subscribe to Android Authority's YouTube channel, and last but not least, don't forget to go over to androidauthority.com, because we are your source for all things Android.